Let us see another problem. Is the function f defined by fx equal to x if x is less than or equal to 1, and 5 if x is greater than or equal to 1, continuous at x equal to 0, at x equal to 1, and x equal to 2. So our function here is, when x is less than or equal to 1, then it is x. When x is greater than 1, it is 5. So here again the function is breaking at the point 1. At 1, the value of the function is x, and at the point less than 1 it is x, and at the point greater than 1 it is 5. So the function is breaking at the point 1. So here first of all we have to check for x equal to 0. At x equal to 0, now if x equal to 0, where does the function lie? X less than 1. X equal to 0 lies in this part. So 0 will be here. So for f equal to 0, it is x. That means it is 0. And for a point, what we said, if we want to check at 0, we have to check at 0. That is f of 0. A point slightly less than 0 and a point slightly greater than 0. Now for a point slightly less than 0 and a point slightly greater than 0, the function is again x only. So if we write it as a whole, x tends to 0, fx will be limit of x tends to 0, the function is x. So if you put x equal to 0, it is 0. Now if we know that the left hand limit and the right hand limit, the function will be the same. For the left hand limit and the right hand limit, the function will be the same, x only. Because if we take a point slightly less than 0 and slightly greater than 0, it falls under this x only, under this function only. So it is enough to write it like this. So at 0 it is 0, and for the left hand limit and right hand limit, we combine it, we write it as 0. Therefore f of 0 is limit of x tends to 0 fx. So it is continuous at x equal to 0. Now at x equal to 1. Now x equal to 1 is the most crucial point we have to check, because our function is breaking at x equal to 1. This is the most crucial point at which we have to check. Now at x equal to 1, what is the value? F of 1 will be x, that is 1. Now for a point slightly less than 1, the function is slightly less than 1, the function is x, and for a point slightly greater than 1, the function is 5. So here the left hand function and the right hand will be different. So limit of x tends to 1 minus fx will be limit of x tends to 1 minus. That means for a point slightly less than x, slightly less than 1, x will be the function. So here the value of x is 1. So 1. And for the point slightly greater than 1, it will be 5. So the function will be 5, which is 5. Now we see that the 3 points are not matching. At f equal to 1, this is 1, here it is 1, but here it is 5. Therefore f of 0 equal to 1, but and limit of x tends to 1 plus is not equal to limit of x tends to 1 minus fx. So the function is not continuous at x equal to 1. We have said that 1 is the most crucial point. If the function is continuous at the point where it is breaking, then for other points it must be continuous. But now since the function is not continuous at this point, now here at x equal to 0 it was continuous. This was the most crucial point where we have to check. Now at x equal to 2, Now f of 2 will be at x greater than 1. So x greater than 1 means it lies here. F of 2 will be 5. F of 2 will be 5. And for f of 2 and slightly less than 2 and slightly greater than 2, the function will be again this only. So if you write it like this, limit of x tends to 2 fx, then this will be limit of x tends to 2 5, which is 5. Here both the values are same. Since the left hand function limit and the right hand limit will give us the same function 5 only, so we write it, therefore it is continuous at 2. So here the function is continuous at 0, it is continuous at 2, but it is not continuous at the point where the function is breaking, that is at 1. That's why if the function is continuous here, then everywhere it will be continuous. Now let us see another question. Prove that f of x equal to cos x when x greater than 0, greater than or equal to 0, and minus cos x when x is less than 0 is discontinuous at x equal to 0. So here we have to prove that the function is discontinuous at, we have to check at x equal to 0. We have to prove it. So at f equal to 0, what is the function? At x equal to 0, it is cos x. That means cos 0. Cos 0 is 1. And for a point slightly less than 0, so less than 0, it will be this function. So if you write 0 minus, it means for a point slightly less than 0, the function will be minus cos x. That means cos 0. Or let us write cos x as of now. We have not. Now we can write, instead of x we can write cos 0. So this is minus 1. Cos 0 is 1, so with minus we have minus 1. Now limit of x tends to 0 plus. That means for a point slightly greater than 0, x greater than 0, this is the function. X, the function will be cos x. So if you put the value of x to be 0, cos 0 is 1. So we see that the left hand limit and the right hand limit are not equal. So limit of x tends to 0, fx, x tends to 0 plus fx, these are not equal. So the function is, therefore the function is discontinuous at x equal to 0. So this is a very simple one. Let us solve one more problem. Question number 19. For what value of k is the following function continuous at x equal to 2? So we are given that this function, if this function is continuous, then here there is an unknown k. What must be the value of k so that this function is continuous? Let's write the function. Fx is 2x plus 1. X is less than 2. When x is less than 2, the function is 2x plus 1. It is equal to k when x is 2, 3x minus 1 when x is greater than 2. So if the function is continuous at x equal to 2, what must be the value of k? Since the function is, or for the function to be continuous at x equal to 2, we must have f of 2 must be equal to limit of x tends to 2 minus fx. That means the left hand limit, and the left hand limit must be equal to the right hand limit. So this condition must be satisfied. So now therefore f of 2 is equal to, when x equal to 2, it is equal to k. Now let us take the left hand limit when x is slightly less than 2. So if it is less than 2, it is the function is x less than 2, 2x plus 1, 2x plus 1, which is, if we replace the value of x to be 2, 2 into 2 plus 1, which is 2 to a 4, 5. Now the right hand limit x tends to 2 plus, when x is greater than 2, the value of it must be 3x minus 1. So we replace the value of x to be 3, 3 to a 6 minus 1 equal to 5. So here f of 2 is k, left hand limit is 5, right hand limit is 5. That means for this 3 to be equal, k must be equal to, therefore k must be equal to 5. Why? From equation 1. Let's say this is 1. Since we are given that the function, if the function is continuous, f of 2 must be equal to this. So from 1 we have k equal to 5. So this is one kind of problem we have done. There can be other problems also of this kind. So it is this, in the same way we can do it.